Okay, so I hear 0, which is correct, right? Because if my D1 is greater than sigma 1 square, this term is always 0. Again, recall our Gaussian, right? If it had higher distortion, if you allow me higher distortion than its variance, then I can just get away with giving it 0 bits, right? So this is just 0. So, and this is the idea, right? So if you, once you give first component the amount of distortion D1, you don't really need to give it extra because you're anyway spending 0 bits to encode it. Like you can't go below than that. And okay, final question is, what will be this rate term if my distortion is greater than sigma 1 square plus sigma 2 square by 2? So it looks very weird, but think of it. My D is like, look at this objective, right? Your total distortion is basically the distortion you're dividing between the two components. Correct? So if your distortion is greater than sigma 1 square plus sigma 2 square by 2, what will be the rate? Like how many bits do I need to spend? Okay, I see at least 3-4 people with faces or hand signs saying 0. So yeah, that's correct. So it's obvious, nothing, no tricks, right? It's 0. Right? Because then in that case, for the first component, I can just allow it sigma 1 square distortion. For the second one, I can allow it sigma 2 square distortion. And then my average distortion in this case would be sigma 1 square plus sigma 2 square by 2. But I know in this case, I'm already spending 0 bits for the first component and 0 bits for the second component. Right? So once my distortion is higher than some quantity, I actually don't need to spend any bits because I've already hit the point of maximum distortion which I can get if I was basically just not doing anything intelligent, not sending anything. Okay. So everyone with me? So again, you can solve this equation exactly, but we just talked about it intuitively based on what we know about Gaussian sources and how you might, like what are some intuitive points here. But now actually, so this is what we talked about. So let's say you actually went ahead and solved it, like you could have solved it mathematically. This is what the solution looks like. And let me walk you through it. It looks a bit complicated, but it's actually not that complicated. So first thing to realize is, like, if you have a RD curve, we can parameterize it by theta. What that means is I can define a theta and then I can have rate as a function of theta and distortion as a function of theta. Okay, so theta is just a single variable and now rate just depends on theta, D just depends on theta. So given a value of theta, I know what my R theta and D theta is. And this is really my rate distortion. Okay. So in that case, the solution to this whole thing, it's just like, again, copy pasted from before, is your distortions I are going to be this minima of theta comma sigma I square. So basically your D1 is going to be minimum of theta comma sigma 1 square. D2 is going to be minimum of theta comma sigma 2 square, such that your average distortion satisfies this exactly. Remember, in our optimization problem, this is an inequality, right? But this gets satisfied exactly. So you can solve this to basically get the value of theta. So given equation 1, equation 2, and equation 3, you can find out what theta solves for this, right? Okay. And then once you solve for this theta, you know what your D1 and D2 is. And then your rate is just plug back. So you plug back, right, just the value of D1 which you got and D2 which you got in this equation. So again, this is half R1 plus R2, right? And you just plug it back. And when you solve it, this gives you your solution. Okay? And this is like, if you have done any optimization course, this is just the Lagrange multiplier, this theta which comes from there. It's not that complicated. It is looking a bit complicated, but trust me, it's not. But we already have intuitively seen what this means, right? So think about what it says here. It basically says, find me some theta. If that theta is greater than sigma, I'll just take sigma 1 square. So my distortion D1 can never be higher than sigma 1 square. This is exactly what we worked out, right? And similarly, my distortion D2 should never be higher than sigma 1 square. It doesn't make sense. I'm already at rate 0 then. And so I need to find, like, what it says additionally is, if your distortion is less than sigma 1 square and sigma 2 square, then your D1 will be theta 1. Sorry, just theta. Let's say your theta is less than sigma 1 square as well as sigma 2 square. Then your D1 equals to, so let's say if theta is less than sigma 1 square, sigma 2 square, then your D1 is equals to D2 equals to theta. Right? This is something which we didn't see intuitively. Okay, and this is like a consequence of solving that problem exactly. The optimization problem. I'm sorry. But the minima parts we saw before. So this is like an additional intuition which you get through the KKT, like when you actually solve it, which is, if my splitting my distortions exactly between the two components always stays below the lower of my variances, then just split it equally. At that point, I'm not doing anything. I could have done anything. I could have split it proportional to variances. I could have split it inversely proportional to variances. I could have done 1,000 different things, right? But you can show mathematically the optimal solution to this equation is if my D is less than, like if my distortion, which I can go, okay, if I can actually split my distortion equally between the two components, let's just do that. Okay? And then this whole minima, etc., is just a fancy mathematical way, which kind of comes about from this exact intuition which we already saw. That if that component gets a distortion higher than its variance, don't give it. Give it to the other one. You don't really need it. This is just like the mathematical way. Yeah. And so this is exactly the water filling intuition. Let's just, this is like the solution to that KKT actually comes up in that particular optimization problem, actually comes up in various different places, and people have come up with this very intuitive way of thinking about this, which is really helpful. And it's called like this water filling intuition. And so let's work it out together, like what I mean by water filling intuition. So first of all, you can agree with me, there are 3 cases I need to work with. First one is when my D is always less than sigma 1 square, sigma 2 square, right? In that case, I can equally split. The third one is when my D is always greater than sigma 1 square plus sigma 2 square by 2. In that case, you know the rate is going to be 0. I can always just split sigma 1 to the first component, sigma 1 square to the first component, sigma 2 square to the second component. Okay? And then this is the interesting one, which kind of makes the previous formula look more complicated than it really is. Okay, so let's just see what's happening. Okay, so case 1. So, okay, let's assume, let me represent my 2 independent components as something like this. This is my component 1, this is my component 2. And what I'm showing on y-axis is sigma. So this is sigma 1 square, this is sigma 2 square. Okay, and again, we assume sigma 1 is less than sigma 2, doesn't matter, right? Okay, so let's see. Case 1, when my D is less than sigma 1 square, and hence D is less than sigma 2 square, right? We assumed. Okay. Let's see. Yeah, iPad is helpful. Don't have to read. Okay. So if your D actually less than this, right? then I can split my D1 equals to D2 to just be half of this, right? Because my D by 2, sorry, this should be exactly D, my bad. Correct, because my D is less than sigma 1 square and sigma 2 square, I can just assign my D1 to be whatever distortion allowed, D2 to be whatever distortion allowed, and then D1 plus D2 by 2 is D, which is less than equals to D, right? So you are within whatever distortion bound. Okay, and then rate in this case, let me write with this. Rate in this case is just going to be half log. Let's write it like this in case it's still not clear. Half of rate 1 and rate 2, like some of them. And then my rate 1 is just half log sigma 1 square by D plus half log sigma 2 square by D. Right, so now you see there is no D1 and D2 terms in our final expression. It's just D, because that's what you want to tell me. You told me that just give D distortion to each one. Okay. Now let's look at the case 2. Okay, so sorry, let me add one more thing. So one way to think about this is assume you had 1 as a sigma 1 square size cup and 2 also as a sigma 2 square size cup. Okay, and so what did you do? It's like assume you poured water into this and there wasn't any barrier between. Then the water would have been basically iso level filled in both these things, right? So it's like you are pouring water equally filled in both. Okay. Now let's look at case 2. When your D is in between, let's say sigma 1 square and sigma 2 square by D. Oh, nice works. Okay. So now in this case, right, we saw that I'll never give D1 more than this. Okay, so in this case, my D1 will be equals to sigma 1 square, right? Because again, like if I were to equally divide, my D would have been somewhere here. It's greater than sigma 1 square, but I'm not gonna waste this much distortion on the first one. Rather, I'm gonna come here and give it to the second one. So my second one would be 2D minus sigma 1 square. So this is just to ensure that D1 plus D2 by 2 is D. Okay, so this plus sigma 1 square by 2 is just D. Okay, and so this is higher than actual D, right? So this is what you would have given if it was equal, but you are now giving the second source some extra distortion. Okay, again, looking at that cup analogy, it's like if I'm filling cups and this was at equal level, my water would overflow the first one, right? If it was more than sigma 1 square, that overflown water kind of goes to the second bucket. So you get like this extra water here in the second bucket. Again, this is just D, this level here. Okay, and your RD in this case again would be half R1 plus R2. But I know my R1 is 0, right? Because sigma square by D, I don't actually need to give it any bits. And my R2 now is log sigma square by the distortion which is given to the second one, which is 2D minus sigma 1 square. This is really my rate. Okay. So basically what did we do? We gave lower distortion to the source which had lower variance. Again, go back to our thumb rule, right? So you gave lower distortion to the source which had lower variance, and you actually gave a higher distortion in this particular case to the source which had higher variance. Okay, you didn't really do it in the first case, and that's really what the formula is saying. Like even though they had different variance, you first try to give them equally, right? Then you try to see, oh, like, do I actually need to give that much distortion to each source? No, I could have actually maybe in this particular case gotten away by giving less. And then you basically allow that distortion to be given to the higher variance source. Yeah.
It's like sigma 2 on the numerator.
Is where?
In the numerator.
Oh yeah, it should be sigma 2. Yes, thank you. Thank you. Did I write it correct here? Yeah. Okay, yeah, thank you. Yeah. And then the final case is now, I would say, very obvious, right? Like, so the final case is just when your D is greater than sigma 1. So actually, yeah, sorry. Sigma 1 square plus sigma 2 square by 2, actually greater than equals to, yeah. Everywhere you can take. Yeah. Okay. And in this particular case again, now you know, right? So it's exactly like water filling, and you would give like exactly sigma 1 square bits here, sigma 2 square here. Whatever extra distortion you are left, you actually don't even need it, right? And your RD is just 0. Again, it's like if you are filling water, it's like you fill the first one till the levels are equal. Then, sorry, you start filling same levels, you are filling both these things. At some point you fill the first one, and whatever extra is coming will go to the second guy. After some point you're also going to fill up the second guy, and you don't really need it, right? So notice this is not maximum of sigma 1 comma sigma 2, right? This can be lower than that. In fact, like APGP, you can show that it will be, not even APGP. Like you can show that it will be lower than maximum of sigma 1 and sigma 2. Okay? And this constant you see here in case 1 was the theta in our equation. We saw that theta, right? When we solved this KKT, we saw that if my D is less than, if I can do that, I'll always split equally. Okay. And so this is like the water filling intuition. Is it clear to everyone, like how you are splitting?
The case 2 should be sigma 1 square less than D less than sigma 1 square plus sigma 2 square by 2 instead of.
Yes, that is correct. Thank you. Yeah, this should be this guy. That's what you're saying. Yeah. Yeah, we'll fix the notes too. I think this might be wrong in the notes also, so we'll fix it. So yeah, so what Siddharth pointed out was this should be sigma 1 square plus sigma 2 square by 2. Same thing which I was saying I should have reflected in the notes, that you don't really actually need to go till sigma 2. Even before that, you can just give 0 rate. And we'll correct it here also. Thank you. Good catch. Okay, but intuitively everyone is with me, like what we did. Again, this water filling intuition is up in optimization case. It's a fancy way of saying, but now you understand what's happening. Like how are you distributing your bits for 2 independent Gaussian sources when you were actually encoding them in blocks of size 2. And so this is again like, so instead of measure, this should be level. So again, remember our thumb rule, which is for a given distortion level, we can allocate more bits to components with higher variance. Okay, because we can allow higher distortion for components with higher variance. And for block of 2 components, we did the same thing. So given, obviously, there is this only case 2 where this kind of comes about, but more generally, you can think of it as that we can allocate more bits to components with higher variance. Okay, and this shows up in various different ways. Okay, any questions? Because now we are gonna use this to motivate the next topic, which is, I would say, very central and integral to a lot of lossy compressors out there. Basically everything, every lossy compressor out there. Okay, I guess everyone's with me, so that's great. So just a few comments. So we looked into a very specific example of uncorrelated Gaussian sources, right? Sorry. uncorrelated Gaussian sources. And like these are just the takeaways. We saw that we can use water filling intuition to basically selectively allocate bits to different components, right? And I'm not going to cover this, but so again, like we talked about stochastic processes, right, when we were talking. So here we just use the block part of the Shannon-Sardi theorem, because where did we use it actually? Like if you have to ask where did we use it, we actually used it when we, where is it? When we did this step. When we wrote it like this, because this half log sigma square by d actually comes from the mutual information, right? So that's where we use the Shannon-Sardi theorem for Gaussian case. But actually what you can show is like it also generalizes very beautifully to like this correlated Gaussian processes, because Gaussian processes have lots of very nice properties. You can use them to decorrelate, and basically whatever we did, you'll add couple more steps to it. And you can show that you can do it for actually a very high dimensional correlated Gaussian sources. I'm not going to cover this here, but look at the notes. That has some intuition. Or if you have done signal processing previously and are comfortable with these topics, we can also talk about it. Okay, but in life in general, we don't have Gaussian sources. We don't have. We'll actually have correlated non-Gaussian sources, right? And we'll probably need to do something more sophisticated than just this water filling. Okay, and that's the idea of transform coding. So transform coding, so this is how I would think about transform coding. There are various different ways to think about it. But the basic idea is you transform the source to a different domain, okay, which allows you to have decorrelated components with different variances. So this is not what transform coding is or the definition. I'm just trying to motivate what we are trying to do. So we are transforming our source to some other domain where we can use the kind of intuition or the thumb rules we got from this Gaussian source, which is it allows you to first decorrelate the components. So that makes your life easier. Not only that, it allows you to decorrelate components with sort of different variances, or a term called energy, which we'll see in a bit, right? And so since it allows you to get this decorrelated component with different variances, now you can, it's not Gaussian, sure, but again, thumb rule. Like you can think of doing the exact same thing which we did with, like which we worked out exactly for Gaussian uncorrelated sources, right? So in the transform domain then, we can use this water filling intuition to now selectively allocate bits to different components, right? So you can be smart about how do I allocate bits to the first component, second component, and that's how you can improve like the compression performance. Okay. So this is just repeat of the earlier slide, right? So we had some symbols, K symbols, encode, codebook, bits, decode, reconstruction. Now I'm going very fast. Hopefully you guys should be able to do the same, right? What we do in transform coding is basically, let's first look at the diagram. You insert a block in the middle before encoder. Okay, so this is some X bar. So this is same as X K tuple, like in the notes somewhere we use X bar. So I decided to continue with that so that it's not confusing. So these are the same things, X K, X bar for now. Okay, so you have some, let's say, K dimensional vector. You first transform this to some other domain. Okay. So, which is just applying this function t to this vector. And now you encode this y, and we go through your same other pipeline, okay? So all you have added is this transform step, okay? And similarly in the decode side, we have this transform inverse, right? So you get y. Now you do all the same things which we have been doing so far, scalar quantization, vector quantization, RD, whatever you want to do. You encode it into a bits, decode it, you get back y hat. And then you can apply the inverse transform to recover your x hat. Okay? For this class, let's assume your t is linear. And I just told you why you would want to do that. Because the hope is, like, even though x has correlated components, y basically you get uncorrelated components with various different variances, which allows you to efficiently encode it. For this class, you can assume that t is linear, but for those of you who are familiar with like machine learning these days, your T need not be linear. It can be something extremely complicated. Pick your favorite large neural net and data. It can be some very fancy nonlinear transform. Okay, and we'll see in learned image compression. Like we're gonna build slowly how we are gonna use this. And during learned image compression, we'll see one example of how you can have some learned transform. Okay. So one way to think about this is your x bar is a vector, right? Your T is a matrix, which gives you y bar, which is again a vector. And then, so if this x was k dimensional, we'll get y, which is k dimensional. Again, the important part really is your T should be invertible, right? So that you can actually recover back x from y. That's really important. This linear thing, this whole linear thing is an assumption, which we'll work with today. Okay. So again, just to repeat once more if it wasn't clear, Y transform coding, right? The idea should be, like, that's really important. So first is decorrelation. So X can be correlated, but once you do all this stuff, like multiplied with matrix, your Y can be decorrelated, right? And decorrelation basically allows you for efficient quantization. So it might have taken you some large vector quantizer to actually get similar compression level, but component simple quantizer like scalar, the complexity of things, right? And then another idea is like energy compaction. And so this is another way of saying that variance idea really. But the idea is like you would ideally want maybe more energy. So we'll define energy in a second. But basically you want more information in some sense in the first component than in the second one. Right? So you can think of it as like, oh, if I'm breaking my thing into two components, like similar to that Gaussian case, I want one component to be something which I really need to preserve. The other one maybe I can throw away. And then what you can do, if you can break it into two components like that, you can allocate more bits and distortion to the more important component and less bits and distortion to the less important component. And that's really the way you steal away performance or bits there. So transform allows for both of these things. So decorrelation as well as energy compaction. So energy compaction really is what's allowing you to allocate bits to basically different components of your block in a more efficient manner. Okay. So like if I have to translate this to our Gaussian case, it's like the source which had a higher variance is more important source for me because it's really hard for me to encode. It can have very high variance. It can jump over. So I'll spend more bits in just understanding that. And then I'll spend less bits if the other one is just always a constant. I don't have to worry, or very low sigma. I don't have to worry about spending bits there. Okay. So these two are like, so again, like T is something which we are designing. Nobody is giving you. You can come up with any T in the world in life you want. But obviously it should serve some purpose to help us with the lossy. So one property we saw was like, okay, it needs to be somewhat invertible. Actually, this is also not hard property because in nonlinear case, these are not exact inverses, but it works out fine. We'll see that idea a little bit more. But then again, yeah, so these are, I would say, not requirements. These are more like, oh, it would be nice to have these properties, right? So if it decorrelates more, great. It helps me, makes my further steps simpler. If I can get energy compaction, again, it then helps me selectively distribute bits better. And so since I am allowed to choose T, my first assumption was, okay, T is linear. Actually, let me make a even stronger assumption that T is an orthonormal matrix. Okay? So as soon as I said orthonormal, I saw some confusing cases, so I'm happy I did this quick review slide. But yeah, so we are gonna use a bit of linear algebra and signal processing in this class again, like we have been doing. It's not, we'll give you the basics. So let's just quickly go over, like, again, this is just, you can take any linear algebra book or notes, and this is like very simple concepts. We'll go over this, but after this class, if you are not able to follow, come talk to us. Like if you don't have background in this, we can give material or explain this better. So I'll be going a little fast, assuming people have seen it and only need revision, not really defining and explaining things from scratch. Okay. Okay, so what are actually orthonormal matrices? Okay, so if consider your y equals to x, ax is just a matrix vector product, then we call A as orthonormal, which will denote as U, if U transpose U equals to identity. Okay, so U is it's a square matrix. Maybe I should have written that. So A is a square matrix. Actually, let's write it. U is a square matrix. Right. Everyone with me, like this is, I can just assume this is fine, right? Anyone? Okay, good. So then the square of the Euclidean norm, it's what's called energy, like what we saw, like energy compaction term really. It's also called energy. And what you can show that it is preserved under an orthonormal transform. Okay, so if you write norm of y square, you can write it as y transpose y. This is just like the definition of norm. This is x transpose, so y is just ux. Let's write it down. Y is ux. Therefore, y transpose is x transpose u transpose. So this is just y transpose. This is y. Just like definitions, not doing anything fancy. U transpose u is identity by our definition. So this gives x transpose x, which is just norm of x square. You can also write this as y1 square plus y2 square plus dot 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 whatever yk square, right? And for those of you who are maybe familiar with signal processing and one specific orthonormal transform, which is this Fourier transform, you might have heard of Parseval's theorem. It's just like a specific case of this particular thing. Like it's just generally true for any orthonormal metric. So, okay. What it really means is that the energy in transform domain matches the energy in the original. And this is really like reading it out in English. Okay. Similarly, what you can show that is this transform preserves Euclidean distance between points. What that means is, assume your y1 is ux1, y2 is ux2, and if I'm calculating the L2 distance square, in this case y1 minus y2 norm whole square, you can show that this is equal to x1 minus x2 whole square. Okay. Again, it's like the same thing, like instead of y here, just put y1 minus y2 and you'll get a u transpose u, which becomes identity, and that will give you this x1 minus x2 square. So just work it out, it's just directly the definition. And this is very cool. So this is what it's really saying is, if I have a mean square error distortion, then my expected value over mean square distortion for symbols x is going to be the same for y. But remember, y is now in my transform domain. And this is why MSE is also like very, you'll see a lot of theoretical work, etc. on MSE being used. It's because like even in this orthogonal transform sense, like you are basically able to predict the same distortion in the, like whatever distortion you get in the transform domain, you can say you'll get the same distortion for the original symbols. So that's a nice property. That means like I can just treat my transform domain symbols as if I was compressing these things, do the best for them, and I know it will translate as is to the original source domain. Okay, any questions? Okay. So another thing which will be useful for the remainder of the lecture is this idea of eigenvalue decomposition or decorrelation. Again, this is a quick review, but if you guys like this just to brush up, again we can give you notes or come talk to us. But I'm assuming you have seen this sometime in life, so this is not me presenting this assuming you have never seen this in life. If you have never seen this in life, definitely come talk to one of the teaching staff, or like we'll send you some material, but yeah. So suppose you have a symmetric matrix A. You can actually decompose that matrix into product of three different matrices. U, this lambda, capital lambda, U transpose, where U is an orthonormal matrix and this lambda is a diagonal matrix. So what this lambda looks like is some diagonal matrix. And then this is all 0, this is all 0. And what you can show is you can compute this decomposition for any matrix A. And when you do that, you can show that your U is basically a matrix of normalized eigenvectors of A. Okay? So for those of you who have forgotten, just as a reminder, your eigenvectors are vectors which, when you apply matrix to that vector, you apply that product, you make the matrix vector product, you get something which scales. So lambda is a scalar which just scales your vector u1. Okay? And so what you can show your matrix U, I'll just write it here, your matrix U will turn out to be u1, u2, ... let's say uk, n. Where u1, u2, un are the n eigenvectors for this matrix. And then your matrix lambda would be the corresponding eigenvectors in the diagonal term. Everything else 0. Okay. And you can select U such that it's orthonormal, so your U transpose U is identity. Okay. So again, like if you are seeing this first time, I know you wouldn't really follow, but the hope is you have seen this some point in your life, and this is just reminding you guys, okay, whenever we saw it, there was something like this. Okay. And so then the main idea really is like how, like you may like, oh, why did Pulkit suddenly started talking about eigenvalues and eigenvectors, right? So main idea is just like you get, doing this decomposition, you get something which is orthonormal, an orthonormal matrix. We can treat this as a transform, right? We'll talk about what A is, but okay, some matrix A, I can get U, which is orthonormal, and then I can use this as a transform. Okay. So let's say I use U transpose as my transform, where I define my U based on this eigenvector decomposition. Then your Y's are U transpose X. Okay. And what you can show is that for these Y's are actually decorrelated. Okay. And how you show is this, like it's also there in this slide. Let me just do it in on U1. So let's say I have covariance matrix for X, which I'm gonna call sigma. Okay, I'm hoping everybody has seen a covariance matrix once. Okay. Let's say my X is d-meaned, so there is no mean. So let's say this is just d-mean vector. So this expectation of X is 0. Okay. Then I can treat this sigma as my matrix A, which was previously, and I can do an eigenvalue decomposition, which will give me U lambda U transpose. Okay. I take this U and I get Y, which is U transpose X. Okay. Now if I look at the covariance matrix of Y, so that's going to be expected value of Y transpose, which is, we'll just substitute. This is like, so my Y is this, Y transpose is this. Did I write something wrong? Okay. Yeah, sorry. And then remember my matrix U is fixed, right? This is fixed. This is not random. So I can take the expectation terms inside, like just linearity of expectations. So this is just U transpose expected value of X transpose U. Okay. And this is just our sigma. So this is, let me call it sigma X just to be very clear. And so this is just U transpose sigma X U. And maybe I should have written this here. What this implies also is U transpose sigma x U is this diagonal matrix lambda. This is just using U transpose U as I. And then you can left multiply and right multiply. Okay. So what you got here is your sigma y as a diagonal matrix. Lambda 1, lambda 2, whatever, let's say lambda n. And so you see the y's now are completely uncorrelated. Okay. So we actually looked into a transform. Which completely decorrelates. So this is a very nice, so we already saw this particular transform, like which I'm gonna call eigenvalue decomposition or decorrelation transform. It already clearly satisfies one of our requirements which we started with, right? Which is it can decorrelate. And how it really worked is it's basically what is it? It's U transpose, where U was just the eigenvalues. U is just a matrix made of eigenvectors of my correlation matrix. So again, this is, if you have seen this before, you know what I did. Otherwise, just go home, read through this a little bit and come back and talk to us. We can explain this further. In the interest of time, I'm going to skip the example, but first I want to give you a punchline really. So the transform, which we really looked at, it has a fancy, it's a named transform. It's also called Karunen-Loew transform. Sorry, French names, my pronunciations may be wrong. It's a very famous transform, basically in signal processing. If you have done signal processing, you might have seen it at some point. So it's exactly the steps which we did. So it's an eigenvalue based linear transform. So it was linear because we were just multiplying a matrix. And it's eigenvalue based because we computed the eigenvalues and eigenvectors, right? And that was the procedure. And something which I want to say without proof is that KLT is actually optimal transform for a given covariance matrix sigma. Okay. What I mean by optimal, so I haven't really defined optimal, like what optimal in what sense. What we mean by optimal really is that it maximally reduces the correlation between the transform components. Okay. So it basically, the output is decorrelated. So we worked in a simple case. You can also have a bit more complicated cases, but it basically decorrelates your output transform. And not only that, what you can show is that they are uncorrelated and they are ordered in decreasing order of variance. So again, if you have done not decreasing order of variance, but basically what you can show is let's say your lambda 1 was greater than equals to lambda 2 dot lambda n. Okay. In that case, you have basically gotten components y1 to yn such that your variance y1 is lambda 1, your variance yi is lambda I. Okay. So does this remind you of something we saw earlier in the class? Sorry? Yeah, like the energy compaction idea, right? Because now my n different components have n different variances. And they are really what it's optimal is they are maximally spread out. You can show that. So if you know about linear algebra, I'll just repeat it. If not, it might go above your head. So you can think about matrix vector factorization as just transformation of your vector, right? Just rotating and changing its length. Your eigenvector basis is basically the basis along which you don't change the directions. You fix the direction and you can show that this is the maximum value you can change your vectors by. And so basically you can show that no matter what transform you would have done, you wouldn't have been able to find a component which had, I'm thinking condition number, I'm trying to think how to tone it down, but basically you can show that the ratio between the maximum and the minimum variance for the uncorrelated components which you would have gotten is maximally, what you can get is the maximum eigenvalue by the minimum eigenvalue. And KLT gives you that. So it's basically saying the n components which you have gotten are like the most spread out they could have been in terms of sigma, which is actually something we wanted, right? We started with energy compaction and it does that. So it's actually giving us exactly what we wanted to do. Okay, I wanted to work through an example in the class, but maybe I am not going to do it now. I'll upload this slide. You guys can. And then so next time we can. It's for us, so looks like this. We'll work it in class next time, so don't worry, but go through slides 1. It's just doing these steps again, but for a little bit more complicated, like something specific. Yeah. We'll do it next time. Okay. But you understand what KLT transform is, why it's nice, why we can use it, and you can connect it back to what we saw for Gaussians and the intuition there. I think this is where I'm going to actually okay. I'm not going to do any of this, but I do want to do this thing. So we'll show you the example. The only part we'll skip today is examples and some more numbers and notebooks. We'll go through it in the next lecture, but I do want to ask, like, can you guys think of any issues with KLT in practice? So we said it's optimal, it spreads out your components the maximum, but any issues which you can think of? And as a reminder, like this is what we were doing in KLT, right? So your transform is the any thoughts? Okay, so let's yeah. Okay.
Two things I can think of is taking an eigendecomposition is expensive, and also I assume we're using like this sample covariance matrix, which might not, depending on the data well, I'm not sure if computing the covariance would be accurate.
Okay, so student here suggested 2 issues. One is we have to calculate this. Oops, I shouldn't have done that. 1 second. Yeah, okay. Yeah, so two issues. Issue 1 is we have to do this step, right? We have to calculate this eigenvalue decomposition. And now think about it. This is not something constant. This is data dependent. So if I have my first block of X, which is maybe consisting of N or K symbols, let's say that's the thing which we are sticking with. I'll calculate this transform. I'll get something. Now when I get the next K symbols, right? I have to again calculate this transform because it's going to be different. Your X there would be different value, right? And you have to keep redoing this. So basically the first point was, now we have to keep reapplying it. For each block we have to do this. And that's because my scheme is data dependent. It's not like my U is a constant. I just designed it once. I can just put it everywhere. No, I have to actually recompute it for all the data. Right? So that's really one of the major issues. The other issue was like, my sigma x, I'm calculating it empirically and it may not be the actual sigma x. Yes, that's an issue, but practice, we can work around. You have to do some estimation. So yeah, but that basically makes it like for a practical source, it may not be exactly optimal. It's still an approximation. Even when you do this much work, it's still an approximation. But the main issue really is that my transform, this U, it's not constant. It actually depends on the data. So for each block, I have to recompute, and then I have to apply this transform, which is like adds a lot of computational complexity. And so in next class, and what you will see is like, you might have heard of techniques like, so this is just summarized answer, but you might have heard in life about like DFT, DCT, wavelets, all of these different kind of transforms in signal processing. And next class we'll see some of them and how that applies. So these are basically the main ideas. These are constant transforms, and they might not be optimal for the specific data, but they are quite optimal for the kind of signals and distributions we see in practice. For example, for images, for sounds, so on and so forth. We'll learn more about it next lecture. Thanks.